All right, so good afternoon, everybody. My name is Maha Haji. I'm an assistant professor at the University of Michigan, where I run the Symbiotic Engineering and Analysis Lab. First of all, I just want to thank the workshop organizers. This is my first NSF workshop, and it's been fantastic, especially as somebody who doesn't do much AI. I've learned so much, so I appreciate that. So for my talk, I just wanted to share with you some of the work that we've been doing on designing offshore systems, optimizing them, and where I think perhaps AI can help us with the challenges we're already facing. Before I start, I want to mention that this is the work not done just by me, but my whole team. So the work featured in this presentation is a number of PhD students, former postdocs, and many graduate students. Kapil up there is graduating and looking for a job, so you might hear from him for some of those postings or postdoc positions. And then funding has been provided by a number of sources. So in our work, I mentioned we're the Symbiotic Engineering and Analysis Lab, and what I mean by that is we adopt this vision of symbiosis for the ocean. So rather than designing isolated offshore systems, we think about systems that can be co-designed, coexist, and co-benefit. And the reason we do that is because these newer systems that we're going to need in the ocean for water, energy, and food, they can't operate in isolation because they need to be more reliable, more resilient, and more effective than prior offshore systems like legacy oil and gas, for instance. And we connect our work directly to what's called the blue economy. This is an ocean economy that aims at the improvement of human well-being and social equity while reducing environmental risk and ecological scarcities, looking at things like how can we get energy from the ocean, how can we get food from the ocean, how can we do transportation through the ocean. And a lot of this taps into many sustainable development goals from the UN, from clean energy and life below water, to sustainable communities and climate action. So the work in my group really sits between this intersection, using engineering to make ocean systems that are more sustainable, resilient, and multifunctional, not just technically feasible, but also beneficial for people and the planet. From a research perspective, we take this and think about how can we co-design and optimize offshore systems to address a lot of these critical sustainability challenges. Specifically, we look at how can we harvest sustainable energy, how can we harvest water and food, and then also how can we design marine robots to support all of these systems. And the motivation is clear. The ocean covers 70% of our planet, and it's rich in these resources, but it's a harsh, dynamic, and expensive environment to operate in. So to be sustainable, our systems must be multifunctional, resilient, and resource efficient. And the challenges of all of these systems are similar. They must handle stochastic ocean waves. The waves change in frequency, amplitude, direction all the time. There's often a strong coupling between the physical design of the system and how you operate or control it. And you have to balance these competing goals, not just cost, but sustainability increasingly. So the challenges of all these systems are similar, and to overcome them, my group looks at how we can do that using computational models, systems engineering, as well as experimental validation. And our goal is to come up with predictive models, optimize systems, and more broadly, design frameworks that we can use for this new economy going forward. One of the biggest challenges is that these offshore systems are really coupled. And what I mean by that, I'll use an example of a wave energy converter to talk about that. So these are two types of wave energy converters I'm showing here. The first one moves up and down in heave. It's known as a point absorber, and it extracts energy from that heave motion of the waves. The second one is an oscillating surge WEC. It extracts motion from pitching that occurs when the waves hit it. And the one all the way on the right, that's actually a point absorber that's been deployed in the ocean by a company called CalWave. So these things are actually being realized right now. Wave energy converters are extremely coupled systems. If we look at the different disciplines that go into a wave energy converter, we have things like its geometry, hydrodynamics, which how it responds to ocean waves, its powertrain or PTO system, control, and structures. And all of these are tightly coupled. For instance, the hydrodynamic performance is impacted by your choice of powertrain. Because of the forces that the powertrain enacts on the energy converter, and the hydrodynamic response influences your powertrain's ability to extract energy efficiently. There's also a coupling between the control system and the PTO and the hydrodynamics, as well as the hydrodynamics and the structures that you need to now build to handle those ocean forces that you're undergoing. And finally, also the PTO forces need to be accounted for in your structures. So traditional WEC design took a very sequential approach, and in this, we might first consider the geometry of the system, then think about its hydrodynamic performance, look at how we design the structures to handle that hydrodynamics, slap on a generator to extract that energy, put a controller on at the end, all with the goal of maximizing power. But when we do this, the decisions of made in a previous discipline limit our design choices in the next one. And so it causes us to reach suboptimal solutions because we ignore these interactions between disciplines, and the results depend heavily on the optimization sequence. And then any adjustments we make in one discipline may require re-optimization. So it's very challenging in this way. In my group, we see multidisciplinary design optimization is a tool that we can use to address these challenges. So instead of considering the disciplines sequentially, we consider them simultaneously with the goal of, let's say, maximizing power. And this allows us to capture the interactions between disciplines to get globally optimal solutions and reduce the need for iterative adjustments. Another way to think about this mathematically is if you were to optimize for one discipline and then a second discipline, you might reach this local optimum for sequential design. But if you could view the entire design space simultaneously, you might get at the MDO optimum, which is very, very different. And we see this as a way to try to bring more design freedom into the design process earlier for longer. So that's really our goal with MDO. And we've had some promising results in our group trying to apply this to these ocean systems. So we've done some work on the design of a single wave energy converter, and doing this, we reduced cost and increased power when we considered geometry, structures, and control simultaneously. We've also looked at wave energy systems that can produce pressurized seawater for reverse osmosis. And when we apply MDO, we can drastically reduce the cost of water produced by these systems when we consider hydrodynamics, system dynamics, desalination, and economics. And we've even looked at how we might site these systems, specifically looking at wave-powered aquaculture systems. So now we bring in biology, the farm size, the wave energy converter, and location. And so we can see we can find optimal sites. But with all of these systems, we were finding that modeling the hydrodynamic performance was really the bottleneck for this kind of optimization. So you can model the hydrodynamics either using computational fluid dynamics, but that's very expensive computationally, so you would not try to do optimization that way, because design optimization requires running simulation hundreds or thousands of times, and that issue is compounded when you consider multiple disciplines as we do in MDO. The complexity just increases. At the same time, when you think about optimization, you really want to leverage gradient-based optimization methods because they're the fastest and they scale better as you add design variables. But the challenge is that other solvers, linear boundary element solvers, which are much faster to run than CFD, are not analytically differentiable. So this poses a challenge to MDO. So we've tried to tackle this problem with a couple new tools. So first we've said, okay, can you get by with an analytical model for the hydrodynamics? So we've done some work on that, and we're working on semi-analytical models for hydrodynamics that are 30 times faster than boundary element methods, and they're differentiable. And then we've also completely rewritten the boundary element method to be differentiable, and this was a collaboration with Sandia, and this code is available now to download in a tutorial if you're interested. But now with this analytical differentiable BEM solver, we can handle a wide variety of geometries, allow gradient-based optimization, and then if you have gradients, I start to think that AI starts to get a lot more interesting, whether that's data-driven methods for AI, whether that's using any neural networks that require sensitivities throughout the design or simulation. So I start to think, what's next, and can AI reasonably help? Well, for all of those offshore systems that I talked about, I see different groups of typologies come about. Systems that talk about renewable energy, systems that extract resources like hydrogen, systems that are hybrids between these, and then even mobile systems like robotics. So could AI help for design representations across this broad landscape of typologies? Could AI also help with design space exploration? I'd love to be able to probe more organic designs to see how they would perform in an ocean setting. Could AI help with that? And then could AI help with the design analysis and optimization portion, which I think has received, probably the most research, allowing us to rapidly iterate between these designs and consider new designs and new deployment locations. And finally, could AI help us with evaluating design metrics, especially these tough ones like the ILIDs, sustainability, reliability, maintainability, all of these that become increasingly important in an ocean environment where we cannot physically go to our structure and test it out, and it really needs to be self-sufficient. So I want to leave you with those questions, and I'd love to hear your thoughts. But if you're interested more generally or are doing work in the space of ocean systems, I also want to highlight we have a special session in ASME IDTC this year on the topic. So thank you.